So that was fine if the radius was equal to 1, if the modulus was equal to 1. My next question is, well, what happens if the modulus is not equal to 1? Okay, so let's start with a complex number that looks something like this. In fact, let me move it to 1 plus I. Let's just keep it simple. Okay, let's go 1 plus I. And let's see what happens if we find roots of 1 plus I. So effectively, what we're trying to solve here is an equation like this. So I'm just going to say a complex number, w, or omega, would be equal to 1 plus I, okay? And I'm basically seeing what happens if I raise this to higher and higher powers. So I'm saying, right, what happens then? Let's just stick with 2 for the time being. What happens if I take a complex number, I square it, and the answer is 1 plus I? So the way which I would solve that, is by taking that complex number and square rooting it. So would you be happy that would be the same thing? That would be the same thing. So let's think about this then. When I take roots of complex numbers, would you be happy now that the radius, or the modulus, is no longer 1? Like the modulus of 1 plus I is equal to root 2, right? It's 1 squared plus 1 squared square rooted. So it's root 2. So 1 plus I is like here somewhere. So it's 1 plus I. Okay? And the modulus of this thing is equal to root 2. Okay? What is my argument? Yeah, pi over 4, right? We've dealt with this enough. Okay, it's pi by 4. Okay, fine. So what I'm literally asking here is what happens if I take the square root of that? Now, would you be happy that according to de Moivre's theorem, that if I raise a complex number to the power of n, effectively I am stretching the complex plane by a factor of however many times that is, and I'm also moving through the argument that many times as well, so I'm rotating as well. So what happens then if I raise this to the power of, well, you're happy this is the same as raising it to the power of a half? What happens then if I raise it to the power of a half? Would you be happy then, instead of stretching it by a factor of n, you're basically taking half of this. So you're basically making it smaller, you're shrinking it down, okay? And are you happy as well that the argument should also be halved? Like you're also rotating it, if you like, in the opposite direction, okay? So watch this on the screen. If I raise it to the power of 2, would you be happy that I get this rotation, and I also get this stretch which is happening as well? So it's moving inwards, and it's also halving. Okay, so the distance between, if I get rid of that, and I get rid of that, the distance between 1 plus I and the square root of 1 plus I, let's just look at the base one first, it will be half the rotation, and it will also be a stretch inwards by a factor of, well, whatever root 2 is to the power of a half. So it'd be 4th root of 2. Is that okay? Kind of, yeah? So basically the argument has been stretched by a factor of a half, or it's been reduced by a factor of a half, and also the modulus has been reduced by a factor of a half as well. Okay? So you've gone from root 2 to root 2 square rooted, so to the power of a half. And you're happy as well that the argument, which was pi by 4, has also been reduced by a factor of a half. Okay, so the new argument will be pi by 8, and the new modulus will be root 2 raised to the power of a half, which is the 4th root of 2. Okay, so that is the new modulus and argument of the square root of 1 plus I. So it's along the same kinds of lines as this. In fact, it's exactly the same kind of lines as this. Can you see that I'm taking r and raising it to the power of n? In this case, n is just a half. And I'm also reducing this. So I'm taking a half and multiplying it by the argument as well. So it's the same kind of idea as what we were doing before.